Okay, hi everybody. My name's Tijmen de Haan. I'm a faculty member here at KUK in Japan. I'm normally a CMB experimentalist, and you might know me from Cosmology from Home 2023, where I gave a general Lightbird talk, or in 2021, where I was representing the South Pole Telescope. But I've gotten really interested in large language models and AI in general since then. And while I still do some CMB work, today I'm talking about my AI project. And so I want to first of all thank the organizers for letting me give this plenary session. It's such a great conference. I always enjoy being here. And I learned so much actually from all of you guys. So this model is something that I built with my collaborators. Together we're a group called Astro Machine Learning Lab. And we're a group of experts in astronomy, cosmology, natural language processing, and we've also got the NASA ADS represented. I met one of these people, Rui, at a conference actually. It was a conference on large language models and physics, and we got talking, and that's how I got connected to these people. And it just goes to show that conferences like this, one of the most important outcomes is the people you meet and the connections you make. I never would have been able to do this work without my collaborators. So let's get into it. I'll talk a little bit about LLMs in general and the rise of AI in the last couple of years. I'll talk about what's kind of the core hypothesis here. What are we thinking with this work? What's the scientific thesis? Then I'll talk about how we made the model, benchmarking results. I'll do a little tech demo showing how to use the model. I hope you enjoy. The name of the model we trained is AstroSage, and I thought it would be cute or meta for AstroSage to write part of its own talk. So here's the AI timeline as AstroSage sees it. Back in the 50s, this field was really born. The Turing test, which I don't think even Alan Turing took all that seriously, but roughly says like if you can pass messages back and forth with someone or something and it looks human to you, then maybe it's truly intelligent. Funnily enough, with ChatGPT, we've passed that test with flying colors at this point. First chatbots, turns out if you just parrot back what someone says to them, it can be quite a useful therapist. Then there was a decline in the interest in AI in the 80s and 90s. These expert systems were quite popular, where you have kind of rule-based AI. The idea being if you implement enough rules, maybe eventually it becomes intelligent. Although again, there was a decline in interest, another AI winter. I'm not sure that this timeline's exactly right, but in 2012, I would say deep learning really took off. Deep learning meaning the use of artificial neural networks. There was this competition, ImageNet, every year, computer vision competition, try to analyze what's in various images, and somebody brought a deep neural network and blew away the competition. So this really sparked the interest in neural networks again. And I would say a real milestone for me in the timeline was AlphaGo, which way ahead of its time beat the game of Go, or at least beat the top human at the game of Go. And really here's where we saw a real classic example of AI creativity. This move 37 in the second game, AlphaGo versus Lisa Doll, where AlphaGo made a move that humans wouldn't have really considered. I'm not so familiar with Go, but I do play chess, and I'm familiar with some of the sort of revolutionary new ways of thinking brought about by modern AI. For me, it begs the question, can we create such a revolutionary change in our way of thinking when it comes to cosmology? 2017 was a paper that's maybe a little overhyped, but quite an important paper that set the transformer neural network architecture as we still roughly use it today. In 2022, ChatGPT launched. This was really a turning point for non-AI people, for the general public, where the advent of large language models, which were around, became quite well known among the the wider world. 2023, I think, is important, where Llama 1 was released by Meta. And this is the first time that a large-scale pre-trained model, the actual model parameters were in the hands of people like me, who could then fine-tune and play with those models. I would say a big milestone last year was the increase in context windows, so the maximum length of conversation you can have with an AI if you like. Gemini demonstrated up to 10 million token context, which is, you can now put a whole bunch of PDFs into the context window and the AI can talk about them. Yeah, I don't know if this is quite humble enough, but AstroSage put itself here in 2025 as another big AI milestone. So one of the things we set out to do with AstroSage was to make a useful model. You can ask it questions, you can sort of talk to it, brainstorm, you know, if you kind of know what the answer should be, like work your way through the logic of it with AstroSage. Maybe it can do some programming tasks for you. It can be an educational tool, etc. But we also sought out to answer a specific ML question. So consider these two axes of different LLMs, one being the vertical one being the resource utilization. I just write compute here, but you could consider the amount of data used or the number of dollars expended. And consider on the horizontal axis how narrowly focused the model is. So up here might be GPT-4o, let's say. This is the model powering ChatGPT at the moment, where it's quite general purpose and it required a large amount of resources. And then AstroSage is down here, which is very narrowly focused. You know, it's only good at astronomy and cosmology, but we didn't have the resources that OpenAI has. And so the question is, what do curves of constant capability look like on this graph? And we don't know, right? What does constant intelligence or usefulness look like? So maybe it looks like this. It could be, right? And so it could be that AstroSage, even though it's very, you didn't use as much compute, it's very narrowly focused, and it could be more powerful than GPT-4o. And so this is the core scientific question we sought to answer with this. Okay, so here's how this model training works. We start with a publicly available model. This is a pre-trained model that is meant for general purpose tasks made by Meta or Facebook. This is called Llama. So we take the Llama 3.1, which is their version, 70 billion parameter model. Then we perform a procedure called CPT, or continued pre-training. This is where we add lots of data like textbooks, all of the AstroPH on the archive, so 250,000 papers from 2007 to our training cutoff, which was January 2024. And so it's textbooks, it's AstroPH 2007 to 2024. And I just did a depth 2 search through Wikipedia for anything Astro related, and I had to use some keyword exclusion to get rid of the least relevant sort of corners of that Astro space. And this gets us our pre-trained model, AstroSage-70B CPT. This model has now seen, through next token prediction, all of this data, and this is the bulk of our compute. This is over 150,000 GPU hours spent. And this model now acts like a base model, so it's able to complete existing chunks of text, and it does not work as an assistant very well. So we then apply supervised fine-tuning, SFT, with a custom blend of data sets, ones that we created, also ones that are publicly available. And this supervised fine-tuning step then gets us an assistant model. AstroSage-70B SFT. And this assistant model is now capable of a conversation. So if you ask it a question, it responds with an answer. If you give it certain instructions, for example, to speak to you in a certain way, to not do something, to talk in a particular style, or if you long answers, short answers, whatever you want, it's now capable of following those instructions. This model now has some weaknesses because of the imperfection of our SFT data set. It just doesn't cover all of the cases that you might, it doesn't have to cover all the cases, but it doesn't cover certain classes of cases that you might encounter while interacting with it. And so we do another step here, and this is model merging. So here we take the bulk of this SFT model, 70%, and we add in some other models. And we use a method called DARE ties, which is a method that is supposed to be quite good at preserving the capabilities of the different constituent models. So we don't think we lose a lot in this step. And then this merging takes the general purpose abilities of the other ingredients that we merge with and adds them to our supervised fine-tune model, creating the final AstroSage-70B model. So let's talk a little bit about training dynamics. This graph shows how the training went, both the long continued pre-training part and the supervised fine-tuning part. I just mentioned model merging, but this is very cheap and does not require a supercomputer time. So there's a couple concepts I need to introduce here. The first is training loss, and the second will be learning rate. And the global step here identifies the number of times that the weights were modified. The top axis here shows where we are in training. So at this point, we start off with Meta's Llama 3.170B model, and then we show it all of the training data, the AstroPH papers, and so on once. Then we loop back around and show it that training data again, do it for a third time, and then finally we swap out the data set for this supervised fine-tuning data set. The training loss here is the objective function. This is what we're trying to minimize, and each of these steps are a gradient-based update to the model parameters. This loss function here is essentially defined as the negative log of the average probability that the model assigns to the token that comes next in the training data. So for example, you have some sentence, the quick brown fox, and then you ask the model, what is your probability distribution over the next possible words in this sentence? And then you go look at jumps and you see, okay, the model's assigning 30% probability to it. All right, I'll put down 30%, and I'll do this for all tokens in my training data set, average those numbers together, then take the negative log of that. And that's what this training loss here is. So if the training loss were 0, that means the model is always assigning 100% to the correct token, and the training loss is infinity, then the model assigns 0% probability to the correct token. What you see is that as the model goes along and it sees more and more data, the general trend is a slight decrease in this loss. So the model gets slightly better at predicting the next word in the AstroPH and other data sets. And what you might think is if the model is doing a really great job at memorizing everything, then as soon as you show it data that it's already seen here at the epoch boundary, you should see a discontinuity. And this is possible when, if you're learning very fast at high learning rate, I'll go into that in a second, then you do get these discontinuities. So we keep the learning rate quite low here. We keep it at the same value as Meta trained their original Llama model. And when we show it the data again, you see no discontinuity. The loss just keeps decreasing. So this is evidence that the model is generalizing. You see here in the third epoch, we had to stop short. We ran out of resources, and we had to actually borrow a little bit of resources to get a little bit more time to do this supervised fine-tuning. The supervised fine-tuning starts off slightly higher in loss, but then quickly decreases and comes down to quite a low value. So it turns out that the supervised fine-tuning data set has somewhat lower entropy, is somewhat more predictable. So the model can learn quite quickly to get lower loss there. At the bottom here is the learning rate. So for those not familiar with this concept of learning rate, it's quite an elementary concept in machine learning. If you think about the sort of second order Newton's method for minimization, right? So this is saying, like, let's assume that locally the loss function is quadratic. So then we'll take the first order moment, which is the gradient, and then the second moment, which is the curvature, and we'll say, given a quadratic, where's the minimum of this function? And then you step there. Then that's the second order Newton's method for minimization, and then there's the damped version of that, where instead of taking a step all the way from where you are to where you think the minimum is, you jump some fraction of the way there, and then you recompute the loss and its first and second moments. This is not exactly how this works. This is a method called AtomW, but the learning rate is that coefficient. It's how much of the way to the minimum do you step, and it's here typically on the order of 10 to the minus 4, 10 to the minus 5. And there's quite an art behind scheduling that learning rate over the course of training. So you can see here at the beginning, I was kind of messing with the learning rate, trying to find the value that I liked, then kept it there for a long time, and then tried to anneal according to a cosine function, taking the learning rate down. Like I said, unfortunately, we ran out of resources here, and then we were able to get a little bit more time on Frontier, and which is the supercomputer we used, and we started doing cosine annealing, but unfortunately ran out of resources again. So this is what this initial period, by the way, is called the warm-up period, and it's where you take very small steps in the beginning in terms of gradient updates, and that's because the particular method we use isn't quite like a second-order Newton's method. It actually has a little bit of memory, so you don't want those initial steps that are uninitialized, where it's trying to find what the first and second moments are. You don't want those to be too large. So this is roughly what the training dynamics look like. Let's talk now about how well the model does, especially in comparison to other models. Best way to get a feel for it, honestly, is to talk to the model for a while. I've talked to it for a number of hours at this point, and sometimes it's very silly and refers to things that refers to the equation or the paper. That's probably my least favorite behavior. That sometimes it's really freaking smart, and it's just very cool sometimes to see the things it generates. I love talking to it for new insights, talking through something where I kind of know what the answer should be or where the endpoint is, and just talking through the logic of something. I find it really useful, and I hope you get to try it and find other use cases for this model. It really does have intelligence in an area that's lacking from the general purpose models, I feel, from talking to it. But how I feel is one thing, and in a scientific context, it's good to have quantitative benchmarks. And so that's what we did. We made a benchmark. Much of this work is done by Yuan-Sen Ting and Josh Nguyen, and they have Josh especially made the benchmark questions. This is a multiple choice question benchmark, and Yuan-Sen did a lot of the evaluating of the public models. The benchmark has over 4,000 questions. It's all multiple choice, A, B, C, and D. And the benchmark was generated from a number of papers that were held out from the training set. So AstroSage didn't read those papers. Maybe the Llama model before it did, maybe the base model had a little bit of knowledge, but mostly the improvements in AstroSage's performance have to come from reading other papers, not reading the same papers that the benchmark questions were generated from in the first place. Over 4,000 questions. These are hard. This is hard, very detailed knowledge. And here's how AstroSage does. So our first model, AstroSage-70B, sits up here around 81% in the number of questions, fraction of questions it gets right. Compared to its base model, that's a massive improvement. So specializing this base model in astronomy, astrophysics, cosmology, and so on, gave it a much higher score. The latest model, the 70 billion parameter version of AstroSage, improves about the same amount. So it takes this Llama 3.170B model and lifts it up here to be the strongest model that exists at the moment for these questions. We tried to be very thorough with making sure that there is no benchmaxing, no cheating, no way to make the model get these questions right other than to really have that knowledge in weights. Here's how the rest of the field does. There are some of the smaller models that are sort of cheaper to inference, and the very largest models that are quite expensive to run. And look at the x-axis here. This is logarithmic. So O3 really is, per question you ask it, much more expensive than our largest model. Yet we do very well on this benchmark. So it seems that our initial hypothesis of can we make a model beat the field by making it very narrow in focus, really reduce down its scope, we seem to support that hypothesis. I should mention that Yuan-sen and myself actually tried these questions ourselves, no Googling, so just answering the questions off the top of the dome, and it was pretty tough. These questions are very specialized about quite niche topics, and let's just say when it comes to stars, I'm an extragalactic guy, so I don't know much. We actually both got roughly the same score. We didn't do all 4,000 questions, but we did significant number of questions, and we both got 2/3 right. So that's 67%, which is down off the bottom of this somewhere. So actually, all of these LLMs are smarter than us in that sense. Okay, let's do a little tech demo here. So I've gone ahead and downloaded the AstroSage-70B model. Here it is. You can see here I have these safe tensors files, which contain the weights, and a bunch of extra files that you get when you download the model from Hugging Face, including the tokenizer and some configuration parameters. I've prepared the OpenAI client straight up, and then there's an OpenAI compatible server, which is VLLM. I'm a big fan of VLLM. It's very efficient, very high throughput given the hardware. I'm running here on a computer that we have here locally. Let me show you. I have here 4 NVIDIA A6000s. These are somewhat older, but they're nice because they have 48 gigs of VRAM each. So 4 of them I can easily run inference on this model. Let's start the server. So VLLM serve, and then the name of the model. So I have here AstroSage-70B. Then I need to specify the maximum model length, which is 8192. Specify the data type, which is BrainFloat 16. Specify the memory utilization the model should try to stay under. This is because there's always some overhead. If you just allow the model to use all the memory at once, it'll give an out-of-memory error. And by specifying 90% of the memory it can use, then it can efficiently build a large KV cache. And one more command, which is the fact that we're splitting this across 4 GPUs. So it's tensor parallel size equals 4, meaning all of those matrices, all those weight matrices get split among the 4 GPUs. So let's start this. Meanwhile, I've started a little IPython notebook up here, the OpenAI compatible client. I start the client here. I don't care about the API key, as this is a local server with no key. The URL is localhost port 8000, which is VLLM's default. Then I have a little script here that turns just a string question into the kind of formatting, the kind of chat formatting that the model was trained on, which is the standard Llama 3.1 chat template, with a flag here for thinking. So if you set this to true, you can get the model to sort of talk to itself for a little while, do some kind of reasoning before answering the user. So if let's set this to false for now. in which case the chat format looks like this. We have a start of sequence token, then we tell it we're in the system role, we give it a system prompt. I just tell it that it's an expert in these various fields, especially cosmology, and to give good answers. Always tell the model what you want is the biggest tip in prompt engineering. If you want the model to be, if you're like, oh, I hate this model, it always gives these long answers, just ask it for a short answer, and just ask for what you want. So now we format a question with this prompt here. I have to write a question, and then we'll call this. We'll create a generator using stream equals true. We can create a generator that will output the tokens as they become ready, and then we'll print the result. So let's type ourselves a question. Prepared one earlier. So I like to ask about my work because then I know whether the answer is correct or not. So this is about a 2013 paper that we wrote where we found B modes in the CMB for the first time, Hansen et al. 2012 in the archive, 2013 in the journal. Let's see what AstroSage thinks. Let's get it to print the answer. It says the first detection of B modes in the CMB was reported in a paper titled blah by Duncan Hansen et al. 2013, published in PRL. This is correct answer. Now, for comparison, let's pull up ChatGPT here, and I'll ask it the same question. Copy, paste, see what it says. Okay, it knows it was SPT poll, but then it talks about Kiesler et al. In 2015, which is after the BICEP2 result. So that's not the first detection. Before that, earlier milestone. So BICEP2 showed B modes first, but somehow 2015 is first. This answer makes no sense. Oh, I see. It's discounting the BICEP2 paper. Well, I would say in this case, ChatGPT gives a clearly worse answer on this question. So let's try a different question. This one, again, is about something that I like to talk about in talks, which is selection biases. The measured SZ mass estimates of galaxy clusters is quite often higher than their later determined masses. What selection bias is this due to? This is a common misunderstanding. A lot of people refer to this as Malmquist bias. So let's see if we can get AstroSage or ChatGPT to fall for the incorrect terminology. We'll print this. This thing says the discrepancy between the measured SZ mass estimates and their later determined mass estimates can be attributed to Eddington bias, which is correct. This is when an intrinsic mass near the survey detection threshold are falsely detected as more massive due to random fluctuations. So you have some noisy observable, and then you put a threshold, and then it turns out that because the mass function is steep, you have more low mass objects scattering into the sample than you have high mass objects scattering out of the sample. And yeah, it looks like this is explained pretty well, although a bit long, although I did ask for a long answer. Let's ask the same question to ChatGPT. I'll start a new conversation here. Oh, the Malmquist bias. Yeah, common mistake. A lot of people call this Malmquist bias, which is about distances. It's about the fact that there's just a lot more volume out in the, when you look further out. And so you have a larger volume to search over, and you'll find more intrinsically bright things, even though they're further away and more dim. So 2 examples for you. There are other examples where AstroSage definitely does worse. Every once in a while you'll get a completion where it hallucinates, it maybe refers to some equation or some article that isn't referenced, and that's due to some errors in the training data, which we hope to rectify for the next version. Should we have the resources to build a next version. And yeah, I hope you enjoyed this tech demo. I'd really love to get this model into your hands. Unfortunately, that costs some online GPUs, which cost money, which I don't have. So at the moment, you can download the model and run it yourself like this. And hopefully I'll find a way soon to make this publicly available for everyone to use. All right, that's it. I hope you enjoyed the talk. In summary, we have a new large language model out. It's called AstroSage-70B for 70 billion parameters. It's very knowledgeable about astrophysics and cosmology. According to our benchmark, the most knowledgeable model at the moment. It has the ability to think before it answers. The weights are out on Hugging Face, so if you have the ability to run your own models, you can try it yourself. I'm looking for a way to make it so there's a website you can go to and talk to it directly. I need to find the resources for that. I'm out of resources for now. I would love to do a little bit more machine learning on this model, perhaps do reinforcement learning. But if you know a way to, if you're connected with someone who has money or compute, let me know. That's definitely the bottleneck at the moment. For inference compute, it would be just a few GPUs that are accessible 24/7. I'll be more than happy to answer any questions you have, either about AI or about experimental CMB. And hope you enjoy the rest of the conference. All right, thanks.